Newton's method for finding the square root of a polynomial, used by both Isaac Newton and Gottfried Wilhelm Leibniz. So suppose we have a polynomial of degree n, capital N, and we want to find the square root of that polynomial. So we're going to find v with the property that v squared is equal to p. And if v is a solution, minus v is also a solution. So we're going to make a 0 greater than 0. So we can compute v squared, just multiply out the terms, but we can rearrange the terms so that they are all powers of x to the k. And then we can equate terms, and we get this identity. Solving for the terms we don't know, and we could say a0 squared is equal to b0, 2a0, a1 is equal to b1. And we can make this a little bit more rigorous. We can take the limit as x approaches 0. We get the first equation, then we can subtract all the terms that we know from both sides, divide by x to the k, take the limit, and we get this final equation, which we already kind of knew was true, but we can think of it as a sequence of polynomial approximations that converge to the final series. So solving for the coefficients, we get these formulas. So what is the rate of convergence, the radius of convergence for v? It depends on the polynomial, and that's kind of an unsatisfactory answer, but it's true. We don't really know. Isaac Newton developed this technique to solve for the square root of the polynomial 1 minus x. And so we'll go through his calculation. We'll go to a spreadsheet and find the first 25 terms of this particular calculation using this technique. So the green coefficients there are the original p, and the yellow ones are the v, and they show up both horizontally and vertically there, because we're going to multiply them out and recreate p. So the v will do the calculations in G and H, those columns. So we'll just equate the k column to the H column. And then the third row, we're just going to equate that to the k column. And that's kind of a tedious task. We have to equate each one by one. We might be able to find a clever way of doing this, but I'm just doing it by hand, just changing each one by one. I'll only do the first 5 terms because it's kind of tedious. We can see the pattern from that. So the first term is the square root of b0. So we know one term right away. And in general, the terms in the interior of this are the products of the two yellow, the row and column. So we can copy that over, and there'll be data in there in just a second, but we'll do the check column. The check just says, well, we're going to see if when we multiply everything out, do we get P back? We should. So far, no, because we haven't put the data in yet. But this is how you calculate the entries. They're the diagonal entries. The next one's going to be the k equals 4, x to the 4th power. This will be x to the 5th power. So it's all those diagonal terms along there. Now, this is G and H here where we do the calculations. Here we're dividing by 2a0. So this is the b sub k minus the diagonal terms in the middle from m equals 1 to m equals k minus 1. So we avoid the two endpoints, but would do all the other diagonal terms. And if we bring this calculation down, it should calculate everything. Yep, that's the first 5, and then here are all the other ones, all the ones to 25, doing it the exact same way that I showed you. This is just showing you what the formulas are in each of the cells. So the p-check ones are all the diagonal terms. And the G is the b sub k minus the diagonal terms other than the two endpoints. All right. There. Newton's rival in the invention of calculus, Leibniz, wrote Newton a letter asking for help in solving a problem. The problem wasn't directly related to calculus. He was trying to find the square root of a polynomial, and he wanted to understand that method. Probably he was trying to solve this problem because it shows up in a formula he was working on. So we will do the exact same calculation, but now for p equals 1 plus x squared. And that's pretty easy to do. We'll just copy the entire sheet into a new sheet. And then we'll just change the p to be all ones. And that's the first 25 terms. It's easy as that. Okay, now the exercises in 1 and 2 have an interesting property. The coefficients aren't rational numbers, just rational numbers. They are dyadic rational numbers. That means the denominator is the power of 2. And you can prove that pretty easily from the formulas. The set of dyadic rational numbers are closed under the operations of addition, subtraction, multiplication, and division by a power of 2, and that's why we can prove that they are dyadic. Okay, you need Taylor's theorem to be able to find the pattern, to be able to prove the pattern. We'll find the pattern, we won't be able to prove the pattern. And I don't think Newton and Leibniz were able to prove the pattern either. I was pretty sure Newton wasn't able to prove his pattern. In fact, that was exactly the question that Leibniz was asking Newton. So we'll calculate this R column, which is the ratio of coefficients. It's K5 divided by K4. And we'll see if we can find the pattern in these ratios. Now that's an interesting number, 7 over 10. That suggests the denominator is 10, and that suggests the denominator might be 2 times k. Well, let's see if that's true. If it's true, then r times d would be equal to n, and n will be an integer. Let's just check and see if that's true. Yes, it is true. So the pattern is really pretty easy to find, and the pattern is, numerator is 2k minus 3. So for exercise 3, the pattern is 2k minus 3 over 2k, and a sub k is this formula involving double factorials. Double factorials are like single factorials, but the numbers go down by 2 each time, so 7 times 5 times 3, etc. Exercise 4, we're going to compute the same thing for the Leibniz calculation. And we'll go back to the spreadsheet. What we'll do is we'll just copy what we did for the Newton calculation. We'll paste it into the Leibniz calculation and adjust the denominator so that we can find the pattern that will make it work. And we don't have to adjust the denominator. It's the same denominator. The numerator in this case is 2k minus 1. And we'll get a formula for r sub k, which is 2k minus 1 over 2k, and then we'll also get a pattern for a sub k, which will come very quickly. You'll see it again right now. Okay, this number can be rewritten as an ordinary factorial and actually a probability. By multiplying and dividing by the double factorials, we're able to turn the numerator into a factorial. And the denominator, you can bring out the 2's, power of 2's. This is the probability of flipping a fair coin 2k times and getting exactly k heads, which is an interesting thing. Why is this probability showing up? And you get this identity, which is true. But what is the interpretation of this identity? I don't know the answer to this question. It's an intriguing identity that I don't know why it's true. Okay, time to close the spreadsheet. Thank you.